Hello everybody, we're going to talk about limits in our introduction to the problems of calculus. One of the first things that we might want to know in order to get ourselves motivated is to ask the question, what are the problems in calculus that it's so necessary for us to learn about limits? And there's really two main problems that we try to solve in calculus. The first one is this. If we have a function and some point P on that graph, we're asked, let's say our point P is right here at 1, 3. We're asked to figure out what is the slope of the line tangent to the curve. This particular problem goes to some things that are done in calculus, such as finding maximum and minimum values, or finding the rate of change of an object at a given time. So what we want to do is figure out, well, what would I have to do in order to get the slope of the line tangent to the curve? And one answer to that was, well, we could estimate on the graph. Just taking a look at this one, looks like it might be about 2 up 2 over 1. But how would we know for sure? Well, we could take another line, pass it through that point right there, and see what happens when we pass it through some other point right here along our line at Q, and then get the slope of that line. Well, you might say that's not a very good estimate. Well, it might be a better estimate if we let that line be a little bit steeper, right? So in other words, we pick some other point that's a little bit closer to P, right? And as we go along, what's happening is that we can choose points that get closer and closer to P. And as we do that, we're letting the difference in the x values between these two get smaller and smaller. And so what we might want to ask here is, how do we ensure that each time we do this, we're getting that slope? Well, this is one of the cases where we need a limit, because we're finding a learning value of the slope as the x values that we choose for point Q get closer to the x value that we chose for P. The other problem that we have in calculus that we try to solve is one using area. How do we find the area under some odd size curve? This isn't a particularly easy kind of geometric figure like a triangle or a square or a circle. And we could come up with all kinds of different estimates. One estimate would be to simply draw some rectangles underneath the curve, right? We could draw a rectangle right here that's about the right size for this little area. We could draw a rectangle here, and we could just keep on estimating until we get enough of the right size rectangles and just see what happens with that area, right? And just add up the areas of all those rectangles. And while it might not be a perfect estimate of the area under the rectangle, we can see that the more rectangles we have, the better our estimate, right? This would be a much better estimate if instead of 1, 2, 3, 4, 5, 6, 7, 8 rectangles, I had 16 rectangles, and I made each of my rectangles smaller and smaller. So if I took all of these rectangles here and just started making them smaller and smaller each time, and then added up all of those areas, I could see that my area would be. In this case, we have another kind of limit that we would be solving. It's a limiting problem of the area of each of these rectangles as the differences in each of the sizes of the rectangles get smaller and smaller. So our motivation here is that we definitely want to be able to figure out what we mean when we say a limit, because that limit is going to dictate how we find the values of the area, or find the value of the slope of the curve at these different points.